Good morning, everyone. Thank you for coming to this session. Today, I'm excited to present our work, VA-MoE, Variables Adaptive Mixture of Experts for Incremental Weather Forecasting. I'm Hao Chen from Hong Kong University of Science and Technology, and I have the privilege to share this collaborative work with my colleagues from HKUST, Huawei, Zhejiang University, and Shanghai AI Laboratory. Let me briefly outline today's presentation. I'll start with the motivation behind our work, then discuss our main contributions, dive into the methodology, present extensive experimental results, and finally conclude with key takeaways. Traditional weather prediction models face significant challenges. First, they require exorbitant computational resources. Second, they struggle with continuous forecast updates as new observations arrive. Consider this fundamental mismatch. Upper air variables like temperature profiles are sparse and sampled via radiosondes or satellites, while surface variables like precipitation and wind are dense but updated in near real time. This asynchrony creates a critical problem. When we need to introduce new variables, say, satellite-derived aerosol data, existing models must be entirely retrained from scratch, incurring prohibitive computational costs that limit practical deployment. So how do previous approaches compare to ours? Previous works require complete retraining of the entire model whenever new variables are introduced. Our approach is fundamentally different. We enable incremental training of only a limited number of parameters from a pre-trained model. This represents a paradigm shift from the traditional full retraining approach. Our work makes three key contributions. First, we initiate the research on incremental learning paradigms specifically for weather forecasting, and we propose a quantitative benchmark to systematically evaluate performance in this new setting. Second, we present Variables Adaptive Mixture of Experts, or VA-MoE, the first framework specifically tailored for incremental atmospheric modeling. VA-MoE achieves expert specialization through contextual variable activation driven by variable index embeddings, enabling dynamic assignment of experts to variables during both training and inference. Third, our extensive experiments on the ERA5 dataset demonstrate that VA-MoE achieves comparable performance for surface variables while delivering superior accuracy in upper air variables. Let me now walk you through our methodology. Our framework consists of three main components. In the initial stage, we process input variables through encoder blocks and decoder to produce outputs. When new variables are introduced incrementally, we expand the input dimension while maintaining the same architectural flow. The key innovation is our incremental module with extra index embedding that enables seamless integration of new variables. The core design shows how surface variables and upper air variables are processed through transformer blocks with specialized experts, where learnable components are trained while keeping the majority of the model frozen. In our incremental setting, weather variables are divided into two sets: initial training variables and incremental variables. When new variables are introduced, we dynamically integrate specialized experts into the transformer blocks. Crucially, we freeze the encoder, decoder, and previous experts, only training the newly added experts and index encoder. This selective training approach dramatically reduces computational overhead while maintaining performance. The heart of our approach is the VA-MoE structure. We introduce index embeddings within transformer blocks that dynamically guide experts in learning hierarchical relationships between atmospheric variables. As new variables are incrementally integrated, corresponding experts are added to the transformer architecture and optimized through index-based affinity assignments. The mathematical formulation shows how we use top case selection with softmax to route variables to the most appropriate experts. This architecture ensures that each variable type, whether surface variables like temperature and pressure, or upper air variables like geopotential height, gets processed by specialized experts tuned to their unique characteristics. We designed a variable adaptive loss function that aligns learning rates with the inherent spatiotemporal characteristics of different weather variables. Our joint loss combines prediction loss, which measures forecast accuracy, with reconstruction loss that ensures the model maintains consistency with current observations. The lambda parameter balances these objectives to optimize overall performance. For our experiments, we used the comprehensive comprehensive ERA5 dataset. We trained our model on 40 years of data in the initial stage and 20 years in the incremental stage. The results show comparative analysis of RMSE across 10 state-of-the-art models for 4 key variables. You can see our incremental learning approach maintains competitive performance across different lead times while being significantly more efficient. This table presents detailed results for surface variables. Our VA-MoE achieves strong performance across all metrics, T2M, U10, V10, MSL, and SP, with only 40 iterations in the initial training phase. More importantly, when we apply incremental learning from 65 upper air variables to 5 surface variables, we maintain excellent performance with just 20 iterations, demonstrating the efficiency of our approach. Even when using a shorter training period from 2000 to 2020 with only 10 iterations, our method still delivers competitive results, highlighting its practical utility in real-world scenarios. For upper air variables, our results are particularly impressive. VA-MoE outperforms many established methods including IFS, HKUST, and GraphCast across multiple pressure levels and variables. Notably, our incremental learning version achieves these results with only 137 million parameters, significantly fewer than comparable approaches while maintaining state-of-the-art performance on variables like Z500, Q500, and T500. These visualizations provide qualitative evidence of our model's performance. The 6-hour forecasts for both upper air and surface variables show minimal absolute error compared to ground truth data. The maximum errors remain remarkably low, just 0.08% for Z500, 0.22% for T850, 1.59% for U10, and 0.47% for T2M, demonstrating the practical accuracy of our approach across different variable types. In conclusion, our work introduces incremental weather forecasting as a novel paradigm that addresses the critical challenge of dynamically expanding weather models without the prohibitive cost of retraining from scratch. While our current work focuses on transforming upper air models to handle surface variables, we recognize the limitation that future work should test performance on larger datasets and extend to broader environmental modeling domains, including ocean and soil variables. Our VA-MoE framework represents a significant step toward more adaptive, efficient, and scalable weather forecasting systems that can evolve with our growing observational capabilities. Thank you for your attention.